Hello, good morning. Let's start a new chapter, the terminal homing guidance. Terminal homing guidance is meaning terminal means the end engagement. We have already studied about the target and seeker, target to seeker engagement. Now, what is happening at the terminal engagement or terminal homing guidance? So, let's discuss about the homing guidance, ballistic guidance, and mid-course guidance. So, in this week we will study about the homing guidance, and later in the next week the ballistic guidance. Uh, so, the purpose of the terminal guidance is to cause a perceiver, which is typically a missile, to hit a target or come close to the target or pre-selected target. So our target is pre-selected, and maybe the target position is unknown, but with the help of homing guidance we can seek the target, and we can apply guidance theorem like proportional navigation, and as well as the terminal guidance. So terminal guidance is analysis of ending the seeker to target engagement at the terminal side. So that's why its name like terminal means the end engagement. Moreover, we require that this interception take place despite unpredictable maneuver, because in this scenario we have a lot of maneuvering error. The target is maneuvering unpredictably, and we have a disturbance and navigation uncertainties. So under these noisy environment and target maneuvering unpredictability, we will have to apply guidance system along with the terminal guidance uh, algorithm. So there are three types of terminal guidance: the homing and ballistic and mid-course guidance. In homing guidance, we have already studied about the homing guidance in the previous lectures, where we have made the following assumption: 1 2 3 assumption. For example, the perceiver is actively controlled during the entirety of the engagement. Okay, with the help of the geometry of the missile and target engagement geometry. Okay, so and the second assumption, the pursuer has a velocity with a constant norm. This is typically terminal phase of engagement, that is closing velocity. We have already studied about the closing velocity. So at the terminal phase, we have to achieve the closing velocity. So closing velocity is a velocity where the target and missile velocity are equal, or where the interception occur. So interception always occur at the point, at the terminal point. Interception always occur at the terminal point where the closing velocity achieved. The third assumption is perceiver is equipped with a passive seeker, that is a heat seeker, or a semi-passive seeker such as laser guided or smart bombs. So with the help of the heat seeker, the line of sight region can be calculated. So under the preceding assumption, we study solution to the terminal guidance problem. So let's study about the solution to the terminal guidance. And you know, we have already studied the geometry of the planar homing. This figure we have already studied in the previous lecture, and similarly, in this lecture we will have to study the terminal guidance, and similarly we have to find the range R and also the beta. Okay, so this is a range and this is beta. These are two important parameters that we have to find in this lecture. So what is range and what is a beta? Okay, so in this figure, all parameters you have already studied in the previous lectures. So in this figure, M is represents the missile, and T is target, and line of sight is represented by LOS, is a line of sight which is created with the help of a heat seeker. So along that line of sight, the seeker try to measure the range, okay, with the help of the sensors. And beta is the line of sight angle. So beta is the line of sight angle, like here, from the missile axis, missile given direction axis towards the line of sight angle beta. Okay, so beta is a line of sight angle, and range, we have to find the range and line of sight angle. And Vm is the missile velocity with the heading angle theta. This is the heading angle theta. So the missile is moving like in this way, okay, with the heading angle of theta. And this is the body axis, or you can say this is the uh, direction axis, fixed. This is a fixed axis. Okay, and so missile, let's have the missile have two components, v alpha m, v beta m. Okay, there's a component, velocity component, which is orthogonal and along the line of sight respectively. So alpha beta m is along the line of sight, and v beta m component velocity is along the line of sight angle, and v alpha m is the orthogonal to the component of the velocity. And vt is the target velocity with the heading angle theta. This is the target, and target is moving like this way, and this making the angle, heading angle theta. Okay, and then with the components, velocity have two components. One is along the line side, and one is here, v alpha t and v beta t. Okay, and r is the range, and that is distance between the missile and target. So you know this equation, we have this equation from the previous lecture. Okay, and because the range is the difference between the velocity of the target and the missile, and this is the line of sight angle rate, line of sight angle rate. Okay, so beta is a line of sight angle. Now this is a line of sight angle rate. Okay, and this is given by this equation. So we have already studied this equation. Now our homing problem is to find the beta and r. So for the pursuer missile and the target of figure number 5.1, find a guidance law for theta as a function of beta and beta dot to cause a collision or near collision. Okay, so you have to note the remarks or important point from preceding problem formulation. It should be clear that homing problem is inherently a final value problem, because we are talking about the terminal guidance. So terminal means the final value problem. This is our final value problem. This is a final value problem. It's very much clear that we care mostly about the relative position of the perceiver and the target at the end of the engagement, because it is a terminal guidance, it is a terminal theory. So here we are finding the final value problem at the end. So that's why we are mostly care about the relative position of the perceiver and the target at the end of the engagement. Hence it is called as the terminal guidance. So in the equation number 1, line number 2, 5.1 means this equation. This is 5.1 equation. uh, equation but two line but two makes it clear that near interception, because we require r tends to 0 as the missile approaches the target, then r is approaching the 0, because r is the distance between the seeker and the target. So as soon as the seeker approaches the target, the r tends to 0. So we have to make sure about r is tending to 0, and similarly beta so tends to 0. Okay, so tends to 0 as soon as interception occur, then r is 0 and beta is 0, because after interception there is a collision, and target is hit by the missile. So we want this result r 0 and beta equals 0. So this equation number 1 require r tends to 0, but we may have run the risk that beta dot tends to infinity, which in practice means that the missile may encounter maneuver limitation, because for example propulsion navigation problem has a maneuver limitation, and it can bear about a small maneuvering limitation, and mostly generally the professional navigation used for hitting the target which is which have some limitation, maneuvering limitation, or maybe target should go in the straight, or target should fly without maneuvering. So this kind of problem has may encounter in maneuvering limitation. So because of high maneuvering, beta dot can tends to infinity. If beta dot tends to infinity, then it means we we were at the near interception, but target always missed, and the guidance homing loop will continue to feedback to the next input and try to again hit the target. And the block diagram of the guidance system with the feedback system continues to relocate the target every time until the range tends to 0 and beta tends to 0. So this is the three interception scenario. Okay, in all scenario you can see that we have uh, target and uh, we have seen the difference between the target velocity and the missile velocity, and due to the difference between the target and missile velocity we will face some overshoot, undershoot and overshoot. But if however if a missile and the target velocity are same, then you can see that we can finally intercept the target. So these are three scenario, and a pursuer always try to intercept a target in this scenario, but uh, if we assume that both pursuer and target have constant velocity, then we represent the time history of line of sight and the three cases. So here for example, here is constant velocity, here constant velocity, but here different velocities. So that's why sometimes the target quickly move around, and sometimes missile uh, quickly move around. Now we have five different strategies for terminal homing. In the five different strategies, we will first study about the pursuit guidance, then fixed lead guidance and constant bearing guidance, and propulsional guidance. We have already studied in the propulsional navigation. So propulsional guidance is the same as the propulsional navigation, and finally the beam rider, and the derivation of the equation are all same. There is no difference to it. So For example, we will study about the perceived guidance and we will derive the equation for the range R and the beta, and we will study about how the range tends to 0 and beta tends to 0 in the perceived guidance. And a similar method will be applied to the fixed lead and the constant bearing and proportional navigation beam rider, except that we have to change the assumption. In the perceived guidance, we have assumed that the missile always heads towards the target, that is theta is equals to beta. So theta is a missile heading angle and beta is a line of sight angle. So in the pursuit guidance, we assume that heading angle, that is the missile heading angle. We assume that, and this is a line of sight, and this is a beta. We assume that beta is equals to the theta. It means that this angle is similar to this one, beta and theta. Okay, and in the fixed lead, we will replace theta by beta minus theta naught. It means the missile always heads ahead of the target. Means if there is a target, then missile is ahead of the target here, and missile is if moving this way, then missile is if the target moving this way, then missile moving in this way. It means head down engagement. Head on engagement. Okay, but in this case, the it may be the head on or tail chase. Tail chase. Tail chase. Okay, so for example, in the pursuit guidance, if the this is a target, so missile can be follow the tail. This is the tail of the target, and this is the head of the target. This is the target. This is the tail. This is the tail, and this is the head. So missile can be here. If missile can here, then it can hit that from the tail side. If missile here, then missile can hit by heading, by head side. So there are two scenarios in this, but here always seeker try to head down engagement, and the pursuit guidance will try to always heads towards the target by either head on engagement or tail chase engagement. So the in fixed lead, some arbitrary heading angle is lead by the line of sight angle beta. Some arbitrary heading angle is leading the line of sight angle. So it's always when the target follows a straight line, there is a straight fixed lead pursuer target trajectory, pursuer trajectory that yields interception from the head side, from the head-on engagement. And then, and the constant bearing, we will replace it. We will consider the beta equals to 0. In this trajectory, the line of sight does not rotate, and the rate of the beta is 0, constant bearing. However, its implementation requires knowledge of the target maneuver. Okay, so this in this in this scenario, we consider that the line of sight angle rate is keep is moving in the same line, is the same straight line, and is not rotating. But however, in this case, target maneuver, because we do not know about the target may maneuver. But in the constant bearing guidance system, which is installed, which is mounted or installed in the seeker side. This is a seeker side constant bearing guidance system, but we don't know target can maneuver. We cannot we cannot stop the target to maneuver. The target can maneuver. So the seeker should have knowledge of the target maneuvering. Okay, but although in the constant bearing guidance system, the line of sight does not rotate, and it means beta dot equals 0. And propulsion navigation, we have already studied about this formula. Okay, same. Beam rider, here the target is tracked by electromagnetic beam from a fixed station, and the missile flies along the beam. Okay, fixed station is based on ground. So from the fixed station, the beam beam is transmitted, and along which the uh, target can be tracked. Okay, target can be tracked by the electromagnetic beam. So in this lecture we will study just about the pursuit guidance. Other two, and this we have already done. Okay, and this is not important. So we in this lecture we study about the pursuit guidance, and the fixed lead and fixed two is your homework. Okay, homework or assignment. Okay, you have to done your assignment, 5 score, the 5 score. So you have to done fixed lead and the constant bearing problem. Okay, so now pursuit guidance. So we know this equation. In the pursuit guidance strategy, let us assume that the target is not maneuvering. That is referring to 5.1. Assume that theta naught is any arbitrary value, heading value is equal to 0, and the vt target velocity is constant. And also let in this pursuit strategy, we assume that theta equals to beta and theta t equals to 0. That is uh, target is not maneuvering. Theta t equals 0 in the fundamental equation number 1, this one, to obtain the equation one, this one. So if you see in this equation, if you put um, uh, theta t equals 0, for example this r, here is r, so theta t equals to 0, then and vt constant, then this will come like a vt cos of beta. Okay, vt cos beta, theta t equals 0. And then if we assume that theta equals to beta, if we put here theta, then theta minus theta is 0, and cos of 0 is 1. So 1 into Vm is equals to minus Vm. And similarly, if you put here beta equals to theta, then sine of 0 is 0. And then here theta t is 0. Then remaining is remaining variables are the vt sine theta, and here beta equals theta, so vt sine theta divided by r. Okay, so if we put the values this one and this one, and keeping the vt constant, we will get this equation number 3. Now this is our important equation. You have to note that if the beta dot is not equals to 0, beta dot is not equals to 0 unless beta is 0. Okay, unless beta 0, beta dot is not equal to 0, that is the perceiver is in tail chase right behind the target, or beta equals to pi 180 degree, that is perceiver is on head collision course with the target. You have to note the following remarks, that in pursuit guidance, the missile always runs during the engagement unless the engagement is a tail chase or head-on interception, that is beta. Unless this values along these values, the engagements always tail chase or head-on interception. With this value, okay, with this value, the engagement always uh, tail chase or head-on engagement. Other than this scenario, missile keep runs during the engagement. Missile keep engaging with a turning rate, with a different turning rate, unless you got the beta equals 0 or beta equals pi. Okay, combining equation 1 and 2 of equation number 3, combine lines 1 and 2 of equation number 3 here. If we combine this one, means r dot and beta dot. Okay, we are combining this function. This is due to the implicit function which is given in the appendix A of the book. We are not interested in this function. Just follow the procedure. The procedure is this, that we have to combine this equation by this term r dot and divide by b dot. R dot means derivative dr, b dot it means db, derivative of beta. So was just we combine this equation. So r dot is equal to vt cos beta minus vm, and beta dot is vt sine beta divided by r. So we have keep the r towards this side here. Okay, so this equation is can be written in this form. Now apply the trigonometric ratio formula. uh, if we separate this thing, it is uh, vt cos beta divided by vt sin beta. So cos over sin beta equals to cot tan beta, and vt cancel, and similarly minus vm divided by vt sin beta, vt sin beta. So 1 upon sine is a cosec, 1 upon sine ratio is the beta, the cosec beta, and we assume that vm divided by vt equals gamma. So we assume that this vm over the vt is the velocity ratio represented by the gamma in this equation, and r is the same. So this equation we can simplify it with the help of some trigonometric ratio formulas, and r is now considered a function of line is at angle beta. Now equation number 4 can be rewritten is in this form. If we cross multiply the r, if we move this r to this side and this beta to this side, then dr over r is equals to this side. Okay, cross multiplying the variables of r and db, then you can get this one. Now integrate. Okay, integrate this thing to obtain the r, because we want to find the r and beta. We want to find the r and beta. Okay, integrate this equation. So the integral of this one is a log r, integration of this one is a log of sine beta, and the integration of this one is a log of 10 beta by 2. This is the integration of the log of 10 beta by 2, and gamma is the same, and plus some constant, integration constant. Now from this equation, assume without loss of generality, assume the beta is between the 0 and pi, because we are uh, considering head on or a tail chase. Okay, so therefore the beta lies between the 0 and the 180 degree. So we can rewrite the equation 7, which implies like this one. Okay, so this comes like if we move this variable to here, okay, then this will be plus. So we can we can apply some logarithm rules. So applying the logarithm rules, we can find that this multiplication of the logarithm r and the sine beta is same as this one. And also then we can move uh, this variable towards here minus. So we can apply the logarithm rule of log r minus gamma log of 10 beta by this one. Okay, so log a minus log b equals to log of a over b. Okay, similarly log a plus log b equals to log of a into b. So this is a logarithm formulas. So and the constant same, hence we can write this equation and this, if we remove the logarithm, and then we can come to this one, and we are the r naught, beta naught, or values of the r and beta at some arbitrary time respectively. This last equation determines the r is a function of a beta. So in this equation number 9, this is 9, if we assume that a missile approaches the target, missile approaches the target, we have r tends to 0. Therefore equation 9 requires that uh, this equation tends to 0. Okay, why? Because let's suppose finding here r, if we r equals to move here this side, it will come like 10 beta to gamma and divided by sine beta. For r tends to 0, this should be tends to 0. Okay, if this is tending to 0, it means we are getting the r equals to 0. So now the sine beta is finite, therefore only possibility for equation number 11 to be achieved. We have to achieve this equation if the numerator of the left hand side tends to 0, which requires beta tends to 0. So if beta tends to 0, this will tends to 0. Okay. So for this equation to be achieved, one possibility is this, that beta tends to 0. If beta tends to 0, this tends to 0, and similarly r tends to 0. Equation number 11 to be achieved, hence for equation number 11 to be achieved, we must have gamma greater than 1. That is the ratio, velocity ratio should be greater than 1. That is, the missile must be faster than the target. If missile is slower than target, then beta will be infinity. Beta will be infinity if the missile is slower, is missile is slower than target. Okay, but if missile is faster than target, then gamma is greater than 1 and beta tends to 0. So we can examine the turning rate requirement of a perceived guidance. In this equation we can find the r, here r, k, k 10 beta, k of the k is constant, 10 beta by 2 and sin beta. Okay, this one r, and use this expression in equation number 3 to obtain the differential equation, because we want to now find the turning rate, that is beta dot. Okay, so in the equation like this one, in equation this one, now put value of r, sorry, this one, we have simplified this equation by this one. Now put the value of r here. Okay, vt sin theta remains same, so vt sin beta remains same, but replacing r, then sin beta, when it comes to this side, then this will be a square. So putting the value of the r in the equation number beta dot, then you can get this equation. Now now as a missile approaches the target, equation number 12 and 14 imply 12 beta tends to 0 and 14 imply that beta is directly proportional to the beta power 2 minus gamma. Now what this means from the consequence of the equation number 15, for gamma equals greater than 2, the terminal turning rate is infinite, and when gamma is equals to, the terminal turning rate is finite, and for gamma less than 2, the terminal turning rate is 0. In other words, we have seen that the missile is required to be faster than the target to intercept. So that's why uh, we have to make sure that gamma, uh, what is the value of the gamma. So in order to make sure that the missile is required to be faster than the target to intercept. However, if the missile is much faster than the target, then it ends up saturating its turning rate and the end of the engagement. It ends up saturating, means it keeps saturating. It will keep saturating its turning rate until the end of the final terminal guidance engagement. So we have to make sure this value, and we can perform the similar analysis of the terminal running acceleration. We have talked about the velocity, but if we talk about the acceleration b double dot, what is the running acceleration b double dot as the missile approaches the target? Equation number 15 implies that this equation number 15 implies if we double derivative this, uh, then beta double dot is directly proportional to the minus beta power minus gamma into beta dot, and this is directly proportional to the beta power 3 minus 2 gamma. Here in this equation, hence for gamma greater than 1.5, the terminal turning acceleration is infinite. If we put greater values than 1.5, then turning acceleration is infinite, and for gamma equals 1.5, the terminal turning rate acceleration is finite, and for gamma is less than 1.5, the terminal turning acceleration is 0. So in summary, we must have uh, this value, gamma greater than 1 or less than 2 for finite turning rate, and this value for a finite turning acceleration. So in the final remarks, because of the requirement in the turning rate outlined previously, pursuit guidance is used only in specific cases where the target moves slowly, gamma is less than 1, for example, airborne missile engagement ship, or when missile attacks head on or tail on. So in section number 5.2.2, we will show that when gamma is equals to um, yeah, When gamma equals to 1, the perceiver has limitation in turning right and missile is negligible. Hello, this is the gamma is very greater than, this is greater than, if gamma is very greater than 1, that is airborne, that is target moves very slowly, and uh, it means the perceiver is moving very fast. For example, an airborne missile engaging a ship, so ship is moving very slow, and gamma is very greater than 1, then it means the perceiver uh, velocity is much high, um, or when the missile attacks the head on or tail on. So uh, so we will show in the next section 5.2, we will show that when gamma is very less than 1, it's very less than 1, the perceiver has limitation in running right and miss the sun is negligible. In the next lecture we will study about the terminal phase analysis, and after terminal phase analysis we will come back to section 5.2.2, where we will study about misdistance analysis. So in the misdistance analysis we will uh, we will show this scenario, because perceived guidance is always used uh, in some specific cases when the gamma is greater than 1 or gamma is very greater than 1. So perceived guidance is always applied to uh, those engagement where the target velocity is slow, either the slow or very much slow. Okay, so okay, take care, bye bye.